All right, welcome back for part two there, folks. I've copied the results so far, and we'll see pretty quickly, hopefully, you can see the first term is just the first thing cube rooted. The second thing is just the second thing cube rooted. Um, and then the last term is a bit of work, but hopefully we'll see the pattern here. This x squared is this thing squared. The 9 is just negative 3 squared. And the middle thing is just that times that and then opposite. And we'll notice that that works in each time. 5 times y and then opposite. This last thing is negative 5 squared. And notice that pattern works in all of the cases, even if they're more difficult examples. And this middle term is the hardest to remember, and this idea of that times that made opposite. The one way I remember is there's only one negative sign in the whole shebang here, and if this is positive, then minus has got to be here. If this is minus, this has got to be positive. They're always opposites of each other. And the reason that's true, if I were to multiply this out, remember I need all those middle terms to multiply out and cancel. So I'm going to have some positive and some negative canceling out. Watch. In this middle one, negative 5 times 5y makes negative 25y, and the 25 times the y makes the positive 25y to put together to get 0 y terms. And it works also for the y squared term there, right? And this pattern holds. So let's see, follow along, guess along if you can, and see if we can do, we got some more complicated ones. I'm not going to, the whole idea here is to skip the factor theorem. So I'm not going to do the factor theorem for these ones. But what do I think of? What's the cube root of this? So if I were to take the cube root of this, what's the cube root of it? I could think of it as 2q all cubed, right? 2 cubed is 8, and q cubed is q cubed. And over here, this is 3 cubed. So I can think of that. What's the first term then? It's going to be 2q plus 3. And now what's the other term? See if you can guess along. Well, the first thing is just this squared. So what's 2q squared is 4q squared. The last term is just the last thing squared is positive 9. Now what's the middle term? The middle term is these two things multiplied and made opposite. So 2q times 3 is 6q. But it's opposite, right? Since this one's a positive, this one's a minus. And there is your pattern, right? And what do we got here? Well, this is what's the cube root of 64a cubed? Well, cube root of 64, and you might need to put these on your calculator. I hope not, folks. Right? Hit that button, then 64, and then equals, and you'll get that's 4. If you have to reach for your calculator all the time, this will slow you down. So what's this? This is the cube root of this part is 4a. The cube root of this part, cube root of negative 27 is negative 3. Now, watch the exponents here. What's the cube root of b to the exponent 6? Oh, that's b squared, isn't it? Right? Cube root of that is that. And I could think of, well, is this true? Is that the cube root? If I cube these things here, does that work out? Yeah, it does, because b squared all cubed exponent rules 6. And so what's the first term in this factoring? 4a. And then minus 3b squared. Now what's the next term? Well, here I'm going to have this thing all squared. So 4a all squared. And if you have to do rough work in the margin over here, you go nuts. So if you have to do this sort of thing, like this is a grade 9 thing or a grade 10 thing, then you go ahead and do that. I'm going to, for the most part, do it in my head because 4a squared isn't so bad. And notice that when I go 4a times 16a squared, I get 64a cubed, and everything should work out. Anyway, the last term is this thing squared, which is 9b to the exponent. What exponent is it? to the exponent 4. What's the middle term? The middle term is the hardest thing. I've got 4 times 3 is 12, and a times b squared. A times b squared. What's the sign here? Well, there's already a minus there, so this has got to be plus. That times that made opposite is a plus. Did you get that one? Well, here, see if you get this pattern. Pause the video and write it down and see if you get it. Okay, I hope you tried it, because here we go. What's the cube root of this? It's 10x cubed. And then it's a minus. And watch your exponents here. What's the cube root of that? Well, the cube root of y cubed is just y. The cube root of z to the exponent 4, or 12, is z to the exponent 4. Cube root, right? And again, check it in your margin. If you can't see it in your head, is this true? Yep, that works. And so then here are the terms that I fill in the rest of the pattern with. That squared is 100x to the exponent, 6. The last term, I always like doing first and last because they're easiest. This thing squared is y squared z to the exponent 8. And then the middle term is that times that made opposite, so it's going to be a plus 10x cubed yz to the exponent 4. Did you get that one on your own? Awesome. Not that bad. Now, I realize, how often are we going to run into an expression like this? The answer is never, except for in today's homework and on the test for this. But the idea is, if you can recognize and apply a pattern for a very difficult one, then you can apply and recognize it for the easier ones. And that's the whole plan here. Okay. So in general, now I want to mention in the textbook, they just do this sort of thing, and they say this is the sum of the cubes, and then they use a. I don't like doing that, because this a could be a whole expression itself. And so I think of this pattern, a difference of cubes is anything cubed subtract anything else cubed. So I think of it like this, and this is going to look weird. So I think of it as, some triangle cubed minus, I'm going to use a different color, some other expression cubed, right? That's a difference of cubes, right? And this idea of it's not just an A and a B, that I could think of this as the triangle all cubed, and then this is the square all cubed. And then here's the pattern then. So this pattern then goes something like this. If I wanted to factor this using a pattern, not using the factor theorem, that the first term is just the cube root of this, and the second term is just the cube root of this, which is just blue square. Then how does the rest go? Well, the first term is this squared, and it doesn't matter what it is. It could be a complicated expression. And then the last term, and I like doing the last term next, is the second thing all squared. And then the middle term, it's opposite, right? That times that made opposite. And there's your general pattern. Now, you're not going to see triangles and squares in your textbook. You're going to say A's and B's, but I think this is more accurate because it's anything cubed subtract anything cubed, not just letters like they have in the textbook. They'll have this pattern in your textbook. All right, well, give a go for the sum of cubes. Pause the video again. Guess the pattern, what it's going to look like in triangles and squares for the sum of cubes, and then I'm taking it up in a second. Pause. Okay, did you give it a go? I hope so. Here's the answer. For a sum of cubes, some good coloring there on my part. First thing cubed, and it's a positive here, right? You cube root the second thing, and it's a positive. Oh, oops, didn't do anything there, right? That's got a no threes on there. I goofed that. Did you fix it? You had it right, didn't you? You got to trust yourself there. All right, and then this is the first term is triangle squared. The last thing is square, square, and the middle term is this times this made opposite. This times this made opposite. Dandy. Okay, so let's put this to use to do some combinations. Last couple of examples here. Factor fully. Notice not a sum of cubes. I see a sum. I see a number that looks like I can divide by cube root it, but I can't take the cube root of x to the exponent 4. So what's the first thing to do? Common factor first in any factoring. Ever since grade 10 when we first started factoring, common factor first. Right? Common factor first. So I take an x out, and then, yep, okay, this is a sum of cubes. In fact, this is very close to the one that we did before. Cube root of that, cube root of that. What's the next term? This thing squared is 4x squared. The last term is 9. Middle term is this times made opposite. So 6x made opposite. There we go. And you can try and look. This looks like it can't. You can factor this, but you can't. This can't factor. All right, so let's try the last one. This is a dandy one, because this is a difference of cubes. I can take the cube root of this. I can take the cube root of that, and the cube root of this is a squared. The cube root of this is b to the exponent 4, and it doesn't seem like it's too much of a question at all. This term is a to the exponent 4. Opposite, I'll do the last term first. That thing squared is b to the exponent 8. And notice you can sort of do a check that when you multiply everything out, the exponents will work out. B to the exponent 4 times b to the exponent 8 will give you the b to the exponent 12 like we're expecting. And the middle term is opposite, that times that. Dandy. So that one was easy, right? Well, if we stop here, we don't get full marks because this is actually a difference of squares, isn't it? This is like a grade 10 one. So what was that pattern? The difference of squares was just the square root of that with square root of each thing with opposite signs. Grade 10 style. And then this stays the same. This still doesn't factor. What's kind of surprising about this, as we'll see, is I could have, and let me change colors here just to say, because we're done here. This is dandy, nice, and a good question because you have to recognize the difference of squares. That I could have thought of this as a difference of squares first. Watch this. So this would be a cubed minus b to the exponent 6, and maybe this was some of your instinct to see this as a difference of squares first. Well, what's going on then? Well, how do I get this other factor? Well, what I have now is a difference of cubes and then a sum of cubes. Right? Factor this thing as a difference of cubes. Cube root of this is a minus b squared, and that makes sense because there's that. But then what do I get when I factor this part? A squared, and the last term is b to the exponent 4, and then the middle term is that times that made opposite. Not 2, there's no 2. That times that made opposite. And then this as a difference, a sum of cubes, factor it. So I'm going to make this jagged. So this one is this one, and this one is this one here. A plus b squared, and then the leftover terms, b to the exponent 4 again, and then the middle term, that times that made opposite. Where am I getting the 2 from? That times that made opposite is ab squared. Oh, dandy. Okay, so look, what do we got here? Check, check. What's all this other stuff? Well, somehow this must factor into this. Somehow a to the exponent 4 plus a squared b to the exponent 4 plus b to the exponent 8 is equal to a squared plus a. And who would see that? Well, I wouldn't expect you to see that. That's pretty difficult. But somehow this factors into this. Now, I know you could expand and check and make sure that that's true. It has to be. But if you can somehow come up with a way to factor this to this, and this is factoring, if you can factor that, then I'll give it, not expand it, factor it, I'll give you a bonus. Write that up, and you get a bonus for that. All right? Because there's a way. It's a little bit challenging, but there is a way. Notice, so on a test, what would happen if I did it this way? Would I still get full marks? Yeah, because the whole idea here, do you know what the sum and difference of cubes is? Yes. Do you know what the difference of squares factors as? Yes. So even if you factored it this way, I would give you full marks for it. But notice that this is more factored. So this is actually the best solution. All right. That's it for today. There's a few homeworks in the FAQ to come, and try that bonus if you are brave and worthy.